friends, welcome to this video. In this video, we are going to discuss about a neural network architecture called autoencoder. Autoencoder are a type of neural network that attempt to copy its input as closely as possible to its output. Its aim is to take an input, transform it into a reduced representation called or embedding. Then this code or embedding is transformed back into the original input. The code is also called latent representation. As you can see here, input image, which is fed into the encoder part of the autoencoder. Then this encoder turns it into a reduced representation called code. And the code is given into the decoder, and this decoder convert it into the original image. But there's always some difference between the original and the predicted image. Let's now discuss some of the point about the autoencoder. First is the data specific compression. Autoencoder compresses the data that is similar to what it has been trained on. An autoencoder trained on dog photos cannot compress human faces easily. This means that if you train an autoencoder on a images of domain 1, that you cannot use it to compress images of another domain. Okay. So second is unsupervised in nature. Training of an autoencoder is easy as we don't need a label data. It can be easily trained on any kind of input data. The third is lossy in nature. There's always going to be some difference between the input and the output of the encoder. Output will always have some missing information. As you can see in this output diagram of the 4, the digit 4 is not clearly same as the input. There's always some difference. So you can read more about autoencoder in this article. The link is given in the description. Now we'll move on to the coding part. Now we'll build a simple autoencoder in the TensorFlow 2.3 version, and the Python is 3.8. Now let's start the code. First of all, we are going to import all the required libraries. Okay. Next is NumPy. Next, we're going to import the matplotlib. And this matplotlib we are going to use check the difference between the input and the output. We're going to plot the input and the output into the a graph and then check them. Next, we're going to import the TensorFlow, the main machine learning library. Next, we're going to import some layer models and optimizers. Okay, we have imported two layers. First is input, second is dense. Okay, we have imported model function to build a model. Next, we're going to import the optimizer. And here we import the Adam optimizer. Now let's seed the environment first. Make sure there's no randomness is there. The same goes with the TensorFlow. You have to random. Okay, let seed. So we'll try to make sure that the results are reproducible. That's why we seed the environment so that no randomness is there. Otherwise, if we train it again and again, then randomness would be there. I will train this. I will get some result, and if you train this without seeding the environment, you will get some different result because the weight are initialized randomly. So we make sure that the environment is seeded, no randomness is there. So we try to make this, but still there are some functions in the TensorFlow which produce some randomness, but still seeding is good. Now we're going to load the data set, and for this we are going to use the MNIST data set. As you can see in the article, load the data. The data set is equal plus data set MNIST. Okay, now it will give us the training images, training label, test images, and test labels. And we only need images, we don't need labels. Xtrain, then data set dot load data. Okay, now we are going to normalize these test images and train images. Train image x train is equals to n divided by 255. So 255 is basically the maximum pixel value. So dividing all the pixel with the maximum pixel value basically means we are transforming all the value of the pixel in between a range of 0 and 1. Same we're going to do with the x test. Okay, so now we have normalized all the images. Let's specify some variable. Height 28. The height and width of the MNIST images are 28 by 28 and channel is 1 as they are a grayscale. Now we are going to flatten all the images. Okay, the training and both the training and testing images. Before that we're going to print their shape. Going to be f string original shape. Now what I'm doing, print dot, okay, and this for the test put, we have the shape information. Now here we are going to flatten them and again print their shape. X train is equals to, here we're going to use the numpy library and the reshape function for numpy library. And here we need to specify the shape in which we want to transform it. First is -1, height into width into channel. So basically we are flattening the input images. Now same with the test. X test equals to, let's just copy it from here, replace x train with x test. Now copy this, print it here, original, flatten shape. Now let's run this code and check. Hope it will run without any error. Okay, so the data set is downloaded. Now you can see the original shape of the data set is 28 by 28 and it has 60,000 images, and in the test it has 10,000 images of the same shape, 28 by 28, and after that we have flattened them, so the number of images remains the same, that is 60,000 and 10,000, but the shape is now 784, that is we have flattened them, multiplied 288 by 288. I think we can remove channel from here. Yes, we can remove this, and now we're going to define the latent dimension. Latent dimension will be 32. So we are going to transform these 784 features into 32. Okay, so this is what latent representation, and again we're going to transform this 32 back into this 784 features, and then we're going to reshape the 784 feature into a black and white image, and then use matplotlib library to display them and compare them. Now let's begin the next part of the code, building the model for autoencoder. Here we're going to build a simple autoencoder, just a really simple autoencoder. Inputs is going to be input shape is equals to height into width into number of, so we can remove the channel, we don't need channel. Right, a comma here. Now h is equals to dense, we're going to use dense layer. Dense layer is going to be of latent dimension, and activation is going to be relu. Basically rectified lineage unit. What it does, it takes the value, if it takes any value, if it is less than 0 then it is going to be 0, if it's greater than 0 it's going to be same as it is. So we can represent as fx is equals to max 0 Now its input is going to be inputs. Now outputs is going to be dense, again a dense layer, capital dense. Now we need these features, 784 features, which are basically height into width, and the activation is going to be sigmoid. So what sigmoid does is give a value between 0 and 1, and as you already know, we have just normalized these image pixels between a value of 0 and 1, so they are basically same. The output should be same as the input, that's why we are using sigmoid here. Autoencoder is equals to model puts, that is the image, the flattened image, and the output. Okay, outputs is missing in. Now let's print a summary and run it. Okay, lot of okay, we haven't specified, we haven't given any. Okay, it should not be here, it should be here. We haven't given any input to this output layer. Now everything is correct. First we have input, then we have a data representation layer. It's inputs, and so everything is fine. Now let's run it again. Okay, you can see model with nearly 51,000 parameter. Input layer is none basically refer to the batch size, so here we haven't, isn't it any information with batch size, so it's going to be the shape. So batch size comma 784 features, transform back them to a latent representation of the size 32, and this latent representation is transformed back into the 784, that is 28 by 28 image. Now let's compile this model. Compile it. Optimizer going to be Adam. Learning rate is going to be 1 minus. The loss is going to be binary cross entropy. Okay, now we can train this model. Training the autoencoder. Autoencoder dot fit. So input is going to be train, and output is also going to be train. Now number of epochs is going to be, let's say, 50. Now let's set the batch size, that is the value for this none. Okay, 250. If it supports, next validation data. Validation data is going to be test comma x. So you can see we don't need any label, we use just original images, and these images can be easily available. You can scrap them. I already have a video on scrapping, how can scrap images from the websites. Click the I button to check that video. You can use that video and learn from it how to scrap images and then use them on the encoder. How fantastic is it? Now let's train it. Okay, before, let's just get rid of all those unnecessary information we don't require. Was to environment if cpp min log level. Now let's start training. Okay, binary cross entropy, unknown loss, no spelling mistake. I'm in so hurry that I make some mistake. See them again. Okay, I can see the training has started, and it's really fast. It's It's going to take 50 seconds. And the loss is really low. It started from 0.27, the training loss, and the validation load is 0.18. And here below you can see really low. Let's write some more line of code till, okay? Let's compare them and check how they look on the test set. Test period by autoencoder.predict on the test set. Now we're going to use the matplotlib library to compare them. Let's say if you want to display 10 digits, big size is going to be 20 comma. Okay, now let's loop. Is first we're going to display the original. Again spelling mistake. Okay, now x is 2 comma n comma y plus 1. Next, to set the title for the ax. Okay, title is going to be original images. The title has been set. Now let's show the images. plt.imshow. Okay, now we need to resize original image as they are flattened, so we need to resize them into height comma width. The grayscale images, we're going to use plt.gray. Get x. False. We're going to do same. So it should be x-axis and y-axis. Now we're going to do same with the reconstructed predicted. Copy this whole thing and paste. And what we're going to change is this first original predicted images. Second is this predicted. Okay, I think that's enough. Now we can save this. plt dot save simple photo encoder.png. Okay, so training has been done, and at the last training loss is 0.0928 and validation loss is 0.916. Okay, training is complete. Let's run this again and run the training again. Won't take, so we can train it again, and this time you can see the comparison between the original and the predicted images. Okay, it's going to complete in 2 seconds, and hope we any. Okay, so we have some issues with the predicted original images. I think the predicted images don't have original images, so let's find out what the issue is. I'm going to check for the issue. I think I got it. I've just directly copied without making one change. This one at the subplot should be, and the first is 2 comma n I plus 1. Okay, then the next it should be I plus 1 plus n. Run it again. Wait for some few seconds and the training would be complete, and we can see comparison between the original images and the predicted images MNIST dataset. You can try this autoencoder on the fashion MNIST dataset and check how different is from this MNIST dataset. You can see this time we didn't have any error. Okay, this time we can clearly see. You can see upper one are the original images and below are the predicted images. So you can see these are nearly same, but they are not fact match. In some case you can see very good amount of information is missing. You can see here upper is 9, but the below one is, I don't think it's, we can say it 9. We can also say that it can be an 8 also, or but isn't it that complete information is missing. So you can increase the amount of data, you can use data augmentation even in autoencoders and train it, see the fact. So that's all about autoencoder. And I hope I was able to give some new information about autoencoders. And if I did, then please grab the subscribe button, like this video and share it with your friend. Till then, have a good day.